In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 3, Yield Criteria, Part 12. In this part, we are going to talk about anisotropic yield criteria. Okay, as we have shown in this figure, we have defined the anisotropy properties of the material before in the introduction, but here I give you a small introduction as well. So as you can see here, we have this sheet metal going under the rollers in the rolling mill, and the thickness is reduced. Okay, thickness is reduced and the length is increased. We are supposing that the width is almost constant. Okay, the width here and width here is almost constant. And we know that all metals exhibit some kinds of anisotropy to a greater or lesser degree when deformed at room temperature. Okay, so this is the rolling direction. We call this the transverse direction. And if we take a tensile specimen in that direction and tensile specimen in that direction, we will have different, and do the tensile test, we will see that we will have different properties like the yield strength or different ultimate strengths in that direction and that direction. Here you can see the grains. Yeah? Here are the equiax grains, but here are the elongated grains in the direction of the rolling. The degree of anisotropy, the difference between the strengths of this specimen and this specimen shows the degree of the anisotropy. Okay, the stronger this difference, the more this difference, the more is the degree of anisotropy. Okay, it says depends on the previous mechanical and heat treatment of the metal, for instance, this metal is undergone rolling. Okay, so flat rolling, so it experiences some anisotropy. Also, in previous operation, this material has gone through heat treatment. So the heat treatment, the mechanical work which has been done on this sheet determines the degree of anisotropy. And anisotropy mostly concerns sheet metals. And there are basically two kinds, namely planar and normal anisotropy, okay, which I'm going to explain in the next slide. So if we have a bulk material, it's very unlikely to have anisotropy, because as we have shown here, anisotropy happens when you mainly due to the rolling operations, and here the grains are elongated. But in bulk forming, the grains are not elongated only in one direction. They may be elongated, but not in one direction, only in one direction. They will be elongated in different directions, and so they will cancel each other out, and we will have same properties in all directions for bulk materials and bulk forming. But for sheet metal forming, this happens. Now, what is the planar anisotropy? Planar anisotropy indicates the variation of mechanical properties in the plane of the sheet metal, like here. That's the transverse direction, that's the longitudinal direction, that's the rolling direction, and that is the longitudinal transverse. It has an angle to the longitudinal and to the transverse direction. So in this plane of rolling, we call this plane of rolling. In this plane, the properties are different, and we call this planar anisotropy. A very common example of planar anisotropy is the earring that occurs during a cylindrical cup drawing from circular blank. This is a sheet metal operation when we use dies and molds to draw a circular blank into a cup. Okay, a cylindrical cup. This cylindrical cup is a very common mechanical part in industry. All kinds of big drawings and drawings, we use sheet metal. I'm going to show you here an example of this. This is a circular sheet. Okay, this is a circular sheet. We have shown it on an inclined plane, and we are showing that this is the drawing that we are doing. Okay, that's the drawing. As you can see, the edges of the sheet metal deform differently. Yeah, and finally, when the cup, this is called cup, when the cup is formed, we have this kind of behavior. Yeah, let's have a look again. This is a circular sheet. I have shown it here as an elliptical sheet, but in fact it's a circular because we are looking at it from an inclined angle, and the die and the punch are working, are not shown here, only the workpiece is shown, and the deformation and these colors are, of course, show the strain. And we can see that finally when the cup is formed, we have these edges which are deformed differently. We call this earring. Okay, planar and it just happens due to planar anisotropy. In other words, if the material properties in the plane of the rolling were the same, this wouldn't happen. Okay, this happens because of the planar anisotropy, and it's called earring because it's like an ear. Okay, the shape of the geometry is like the shape of the ear. Normal anisotropy. Normal anisotropy, when we measure the properties of the material in the normal direction and compare it to the properties in the plane, then we will see that they are different. And that is also called anisotropy. So these are the cons of anisotropy. The strength of the sheet metal through the thickness, allowing the normal to the rolling plane. Okay, along here. So the strength relative to its strength in the plane of the sheet is given by the normal anisotropy. Most frequently used anisotropy parameter is the normal anisotropy ratio. So in order to measure the normal anisotropy, we use a value called R value, which represents strength ratio in sheet metal plane and along its thickness. It is determined experimentally, usually as mean constant numeric value, because we could measure this R value, as I said, is a ratio. So in the sheet metal plane and along the thickness, so we could have in the sheet metal along different directions. That's why it says that we get the mean value. Okay, and the R value, the plastic strain ratio, is called of the sheet metal intended for deep drawing application, is a measure of the resistance to thinning or thickening when subjected to either tensile or compressive forces in the plane of the sheet. It is the ability to maintain thickness as the material is drawn. I would like you to notice this sentence here. It is the ability to maintain thickness as the material is drawn. That is very interesting. Okay, it means that when the material is drawn, because what is drawn? The blank, the sheet is drawn into a cup. Okay, so when the material is drawn, if the thickness remains constant, it means that the resistance to thinning is very high. Okay, why we say resistance to thinning and thickening? Because in the previous slide that I showed you here, let me just draw this, play this again. Okay, if you have a look at this blank, this is blank. Now if we are drawing it inside the die, now I stop it here and have a look at it. Now, in the walls of the cup, we are saying that the resistance to thinning shows the strength of the material in the thickness. Okay, so thinning we understand, but thickening, why we say thickening? It becomes thicker because in the flange, in here, the flange, we call this flange. In the flange, the material becomes thicker because there are compressive stresses here, hoop compressive stresses. Okay, here we have hoop compressive stresses. As you can see, some thickening is happening here, and so generally the resistance of the material to the flow. Okay, if it doesn't flow in the thickness direction, we say that the strength in the thickness direction is high. As much as it flows in the thickness direction, we say that it's weak in the thickness direction. So that is a measure. Okay, as we have mentioned here, plastic strain ratio is a measure of the resistance of thinning or thickening. Okay, we can talk about this more in the tutorials if you like. Right, now then, let's have a look at some models which have been presented by different scientists. One of the very famous scientists is Rodney Hill. I have mentioned him before. He has a book which is called Mathematical Theory of Plasticity, and that book has been published in 1950, and still almost after 70 years it is the basic formulation for the engineering plasticity, and it is being used, still it is being used in the papers published every day. Okay, so the basic of the plasticity is due to Hill, a theory of the yielding and plastic flow of anisotropic metals, which has been published 1948. Quadratic Hill yield criteria has been presented, and it is in this form. Okay, that is the Hill's yield criteria. It's called quadratic because the degree 2 here we have, and we have these constants F, G, H, L, M, and N. Okay, so this function is equal to 1. Now these are the constants that can be determined experimentally. How do we determine it? For instance, we do a tensile test in one direction, in another direction, in the third direction, and we get the values for the yield stress because if the material is anisotropic, the yield strength is different at different angles. Okay, so we get these values, and from those values, substituting into this equation, we can get these constants. Okay, so here we have said that these constants that have to be determined experimentally, and sigma ij are the stresses. Sigma ij, you know, in some notations put x, y, z instead of 1, 2, 3, but here we have put 1, 2, and 3. These are the orthogonal axes. Okay, 3 axes perpendicular to each other. So you can put, for instance, here you can put sigma xx, sigma yy, sigma zz, sigma yz, sigma zx, and sigma xy. Okay, doesn't make any difference. It's just a notation. So sigma ij, either 1, 2, 3 ij or xyz are the stresses. The quadratic Hill yield criterion depends only on the deviatoric stresses, just like the ordinary yield criteria only depends on the deviatoric stress, but of course due to these constants it gives you different yield values at different directions. Okay, and it's pressure independent, obviously. Also, Washinger effect is not considered here. So it predicts the same yield in tension and compression. Notice that we are saying that in one direction it gives the yield stress value the same in tension and compression, but in another direction we will have the same tension and compression in that direction, but the two directions give two different values for yield. Okay, so that's how it works. And anyway, notice that when we were deriving the yield criteria, we put some conditions. One of those conditions was that the material is isotropic, independent of the direction of the loading. But here, it depends on the direction that we test the material. So I said at that time that I will incorporate the anisotropy and Bashinger effect later. So here we are going to incorporate the anisotropy properties. Of course, we still neglect the Bashinger effect, but I will talk about that later. Right. Now, this equation, if we put these constants equal to each other like that and put it in this equation, you get the isotropic conditions which we usually have in the yield criteria. Okay, you can put this LMN here. We can put all of these equal to 3F. Okay, LMN, we put L equal to 3F, M equal to 3F, N is equal to 3F. And here we got F, so we put G is equal to F and H is equal to F. So we get this equation. Okay, and if I simplify this equation, of course, how can I do that? I can do a test like torsion, and we get pure shear in torsion. So if we get pure shear, then these values for the shear stresses are equal and equal to K, which is the yield in shear. Okay, the yield value in shear. So sigma 1 is minus sigma 2 equal to K, and sigma 3 is 0, because for the torsion test that's how the stresses are. And obviously the normal, these other stresses, sigma 1, 2, sigma 2, 3, sigma 3, 1 are 0 because we have pure shear. Okay, and if we substitute these values in here in this equation, then I get that, because sigma 1 and sigma 2 is K, and these are all 0, and it comes to F equal to 1/6 K squared. Okay, so for pure torsion, for pure shear test, we have obtained F, and obviously here L and N are equal to 3F, and G and H are equal to F. So that's what we get. Okay, that is what we had before for the Mises criteria. This was the Mises criteria. Okay, so 1/F. So for the complete isotropy, we get the Mises criteria in here like this. This has been obtained before for the Mises yield criteria. Okay, then let's get back to the quadratic Hill criterion, which is this one, and see what we can do with it. Now, with the axis of material and isotropy assumed to be orthogonal and using tensile test results, we have this. What we are saying here, that we are using the orthogonal axis, and we are taking our specimens along those axes. Okay, so axis of material and isotropy means that we get the axis in the direction of the specimens, or the specimens in the direction of the axis, orthogonal axis. So if we do that, then tensile test is a uniaxial test. Okay, so only we have stress in one direction. Okay, supposing we take the specimen along the x-axis or one axis. Okay, 1, 2, 3. We have three axes called 1, 2, 3, or x, y, z. So if we take them along axis 1, then all the other stresses are 0 because we have uniaxial tensile test. So sigma 1, 1 we have only. What is this y? Because we test the material until it yields. So that is the yield value for the uniaxial tensile test in the direction of 1 or x-axis or 1, axis 1. Okay. So if we put all of the others equal to 0, we get g plus h sigma y, sigma 1, 1 y squared equal to 1. Similarly, if we take a specimen along axis 2 or direction 2, then if we test that material, we get different yield value, which is called sigma 2, 2y. This is different from that. When we had isotropy, all these yield values would be the same. We call them sigma y. But here, in each direction, we have a different value for the yield strengths. So we get sigma 1, 1 here, sigma 2, 2 here. Similarly, sigma 3, 3, and all the other terms are 0. When we are testing in the direction of 3, then all these, obviously these are shear stresses 0, and normal stresses sigma 2, 2, 1, 1, 1, 1, 2, 2 are 0, so we get only two terms, this one and that one, f and g times sigma 3, 3y squared equal to 1. So we get these values. Therefore, we have three equations, three unknowns, f, g, h. Okay, so we could write f, g, h. We could determine f, g, h in this manner. Okay, f is equal to half 1 over sigma 2, 2 y squared plus 1 over sigma 3, 3 y squared minus 1 over sigma 1, 1 y squared. Okay, due to this equation. And as we obtain this, and from this we obtain these three values for f, g, and h in terms of yield strengths in three directions: sigma 1, 1, sigma 2, 2, and sigma 3, 3. Right. Similarly, for pure shear test, constant torsion test, we could do the pure shear, and if we do the pure shear, then the yield value in shear, we have called it tau y in the direction, in these directions, and then the normal stresses are 0, and we get only the shear values. So here we have L, M, N. Obviously, when the normal stresses are 0, the other two shears are 0, we get only 1, and here and there. So we get these values, 1 over the yield in shear in that direction, and in this direction. So all these values are known for L, M, and N, and we can substitute back in here. We obtained F, G, H from the previous slide, and we obtained L, M, N from this slide. So if we substitute for these values for F, G, H, L, M, N, then we have our yield criteria for anisotropic materials, which we can use it in our theoretical works. In here, for the situation where the principal stresses are aligned with the directions of anisotropy, we have written the previous equation in this form. Okay, we have written it in this form. F is equal to, that is the function, yield function, and F sigma 2 minus 3, sigma 3 minus 1, sigma 1 minus 2 minus 1 equal to 3. Here we have used the principal stresses, so in the direction of 1, 2, and 3. And we have supposed that principal stresses are aligned along the direction of anisotropy. Otherwise, we have three orthogonal directions, 1, 2, and 3, and we have taken our specimens along those directions and test them. So we don't have, obviously we don't have any shears here because these are the principal stresses, and on the principal planes we don't have any shear stresses. Shear stresses are zero on the principal planes that we have explained in chapter 2. Now assuming the associated flow rule, remember I explained to you what the associated flow rule is and what the non-associated flow rule is. Associated means that the flow rule is related or associated to the yield focus, okay, and yield function. So we show it like that. Epsilon I, 1, 2, 3, that's plastic, and that is the rate of a strain. So that means d epsilon over dt. Lambda, we said that this is a instantaneous constant, so that's d lambda dt, and partial f over partial sigma I, and f is this yield function. Okay, now we used this before for the isotropic yield function, but we can similarly use it for anisotropic yield function, because as far as we have any yield function, this is true for associated flow. So we can write this obviously in this form, because this is the rate form of the strain. Now if you write it d epsilon I to the d epsilon I plastic, and dt, d lambda dt, partial f to partial sigma I, and therefore if we cancel out this dt and bring the d lambda over here, we get d epsilon I plastic, d lambda partial f over partial sigma I, and we could put f in here. Okay, put this function f here relative to sigma 1, sigma 2, and sigma 3. Do the partial differentiation. So if I do the partial differentiation relative to sigma 1, put I equal to 1, then I can do the partial of this relative to sigma 1, and I get what here is 0. We got sigma 1 here, and we got sigma 1 here. So I get 2g plus h sigma 1 and minus 2h sigma 2 minus 2g sigma 3, because this is to the power of 2, so we have here 2 sigma minus 2 sigma, because if we expand this we have sigma 3 to the power of 2 sigma 1 to the power of 2 plus minus 2 sigma 1 sigma 3, and similarly for this one. So that's why we have these terms. You have to expand them and then differentiate them. So similarly for sigma 2 and sigma 3 we could do that, expand this parenthesis and differentiate it to relative to partial differentiation relative to sigma 2, and we get these expressions. Okay, what are these expressions? For epsilon plastic strain components, plastic strain increments in the direction of 1, 2, and